All right, this is a debrief on the December 2020 physics CP test for student request. Partial debrief anyways. So I'm not fond of going in detail over which multiple choice question there is, but you should be able to recognize that a large object moving quickly should have more momentum than a small object moving slowly. There was a problem where it said, here's a large object heading towards you and it has this much momentum. I can shoot a small object towards it and it has this much momentum. How many of these would it take to stop this thing in its tracks? Well, this momentum divided by that momentum will tell you how many of these you need to shoot in order to stop this thing in its tracks. Free body diagrams show all the forces acting on an object. And anything that's moving at a constant speed has no net force acting on it. Of course, you should know that impulse is the product of force times time, and change in momentum is mass times change in velocity. If you're in free fall, of course, that means the only force acting on you is the force of gravity. Momentum is always conserved in any collision. Sometimes you students goof where something is going to the right and then it rebounds to the left. You need to recognize that the change in velocity is a negative number minus a positive number in a situation like this. If I have a person and they throw a ball, the person's initially at rest, the ball goes that way, the total momentum before they separate is zero. So the total momentum after they separate still has to add up to zero. And whatever momentum the object has going forward, the recoil momentum of the person has got to be equal in magnitude to the momentum of the object going forward. Of course, watch out for your Greek prefixes. If I say the mass is in grams, you should be thinking, well, I know that there are 1,000 grams in 1 kilogram, and therefore you might want to convert the mass to kilograms. Same thing with going kilometers per hour. You should be able to convert that to meters per second if you need to for a calculation. Of course, there are the trigonometric relationships that you should be applying. If you have a hypotenuse, an angle theta, the adjacent side, the opposite side, you should know SOHCAHTOA. For circular motion, we had the formula centripetal acceleration is equal to v squared divided by r. Of course, momentum is mass times velocity. There was a problem where I had an object and it was originally going at some speed, let's say 10 meters per second. And it had a mass originally, let's say 50 kilograms. Let's say there's friction of 200 newtons and an applied force of, let's say 500 newtons. After a time of, let's say 15 seconds, what will be the new speed of the car? Okay, well, so the initial speed of the car's 10 meter or box, whatever this is, object, was going 10 meters per second. 500 newtons being applied with 200 newtons of friction means the net force would be 300 newtons. The impulse would be force times time. And in this case, the net force would be 300 newtons. The time is 15 seconds. So 300 times 15 means the impulse would be 4,500 Newton seconds in this example. Impulse is equal to the change in momentum. So if I divide this impulse of 4,500 Newton seconds by the mass of this object, which is 50 kilograms, I end up with a change in velocity of 90 meters per second. If I start at 10 meters per second and I change by 90 meters per second, then my final velocity would be 100 meters per second. There was a problem where there was an object and it was moving and it hit another object that was the same, no, half the mass. Okay, so maybe I should make this thing look a little smaller. So let's say this thing is 20 kilograms and it's moving at 40 meters per second. And this one here is only 10 kilograms and it's initially at rest. In the problem that was made up, the first object stops completely and the second one moves off. And the question is, what is the speed of the second object? Well, momentum has to be conserved. So the first object, 20 times 40 is 800 kilogram meters per second, has to be the mass momentum of the second object if the first one stops completely. 800 divided by 10 is 80 meters per second. Or in more general terms, I have two objects, one's twice the mass of the other. Whatever speed this one comes in, when it collides with the second one, if the first one stops, the second one goes off at twice the velocity that it was struck. Again, a very common error is if you have an object and it's moving to the right, let's say it's 30 meters per second, and then it bounces and it goes off to the left at, let's say, 10 meters per second. The change in velocity in this situation is not 20, it's negative 40 meters per second. Let's say I have an object and I give it a mass of 1 kilogram, and I don't know how fast it's going, but it hits and sticks to a second object that has a mass of 1.5 kilograms. And afterwards, these two things move off at, let's say, 3 meters per second, final velocity of the two of them stuck together. The question is, so what was the initial velocity of the first guy? Well, momentum is conserved, not kinetic energy, momentum. So if this is 1 and that's 1.5, then together they were 2.5 kilograms moving at 3 meters per second, which is 7.50 kilogram meters per second of momentum. That must have been the momentum of the first object before they collided. So 7.50 divided by 1 means the initial velocity must have been 7.50 meters per second. There was a problem about a box, and let's say this box has a mass of 20 kilograms and it has an applied force. Let's make it 300 newtons at an angle of 20 degrees above the horizontal. And there's some friction. Let's say there's 40 newtons of friction in this problem. And the first question is, so what's the net force acting on the box? Well, you have to resolve the applied force into its horizontal and vertical components, and it's the horizontal component that you care about. So that would be the cosine function. I make it 300 newtons times the cosine of 20 degrees yields a value of 282 newtons. That is the x component of the applied force. That's just the facts, man. Now there's friction of 40 newtons. So I have to subtract 40 newtons of friction from this horizontal applied force, and I have a net force of 242 newtons to the right. The next part asked, well, if it moves, let's say 4 meters to the right, what is the net work done on the box? And the answer is work is the product of force dot the distance that it moves, the displacement that it moves actually. So if I go 242 times those 4 meters, I get the work done of 968 joules of work. So net force, net work. Notice that the mass of the box isn't even used in this problem. And then there was a problem that said, okay, now what if I have this box and it's moving and I tell you it has 1,250 joules of kinetic energy, and then it runs into a spring and the spring stops it. And I tell you, oh, the spring constant is, let's say, 225 newtons per meter. The question is, how far is the spring compressed in a situation like this? And the answer is, all of this kinetic energy becomes stored spring potential energy at the end of the problem. So we don't even need to know what the mass is of the box. What we need to know is what is the kinetic energy of the box. And then the formula for spring potential energy is 1/2 kx squared. This k, don't confuse it with Boltzmann's constant in electrostatics. This k is the spring constant. And in this problem, we're solving for x. So x would be the square root of 2 times the total energy, which is 1,250 joules, divided by the spring constant, 225 newtons per meter. Then take the square root. I get 3.33 meters is the distance the spring is compressed while stopping this object. And finally, if I take a ball and it has a mass of 3.21 kilograms and I raise it up through a height of 4.56 meters, what is the change in gravitational potential energy? Ugh, that's just mgh. So this would be 3.21 times 9.8 times 4.56, enter, and I get 143 joules. This ends my debriefing on that physics test from December.